In this video, we'll discuss the basics of ketals and acetals. To understand ketals and acetals, we must first understand how hydrates are formed. Hydrates can be formed starting from a carbonyl group, that is a ketone or an aldehyde, in the presence of either acid or base. We'll first look at its creation in a base. Starting from hydroxide ion, and in this case a ketone, the hydroxide will attack the base of the carbonyl group, forcing the electrons in the double bond to the oxygen. This will add an alcohol to your molecule and create an alkoxide ion, which can grab a proton from water which is present in the reaction vessel. This produces a geminal diol, or a hydrate. The hydrate can also be reversed in the base. The base, in this case hydroxide, can grab a proton from one of the alcohols, creating an alkoxide ion, and the electrons from the alkoxide can move into the single bond to create a double bond, eliminating the other alcohol. It's worth noting that OH- hydroxide is a bad leaving group in substitution and elimination reactions. But this is a special kind of elimination reaction, where the substrate is already negative, and my leaving group will leave negative. So since my substrate and my leaving group are essentially the same, this is an okay leaving group in this reaction. This is the overall formula for the creation of a hydrate in base, its overall reaction. From an energy point of view, the products and the reactants are essentially the same. There are two neutral oxygens and a negative oxygen on both sides of the reaction, where water is used in the initial forwards reaction, but not in the reverse. However, the equilibrium lies significantly to the left due to entropy. 3 molecules has turned into 2. The equilibrium lies so far to the left that if you were to place a carbonyl group in basic water, you will see essentially none of the hydrate. If that's the case, how do we even know that hydrates exist? We can determine this by using labeled base. If my hydroxide ion is labeled, then my labeled hydroxide will attack the base of the carbonyl group and add itself to the molecule. This will proceed to then form the hydrate, where one of the alcohols is labeled. In the reverse reaction, which is occurring in the equilibrium, hydroxide present in the reaction can remove either of the protons. If it chooses to remove the proton on the labeled oxygen, then the labeled oxygen becomes the carbonyl. So we can see a shift as our ketone, which was unlabeled, turns into a ketone, which is labeled. And this occurs over time, just as the reaction vessel sits. There are also shelf-stable hydrates. These hydrates are stable due to the inductive effect of the fluorines and the chlorines, which are stabilizing the carbon group. Specifically, the one on the right is a hydrate that you may have heard of. This is chloral hydrate, also known as a Mickey Finn, a classic knockout drug used in old detective mysteries and novels. Hydrates can be formed in acid as well. In an acidic solution, the oxygen in the carbonyl group will pick up a proton. Then it will resonate, forming this resonance structure. From here, water, which is present in the solution, can attack the carbocation that is formed. Water, which is still present in the solution, can grab a proton to form the hydrate. This reaction can also be reversed in acid. One of the alcohols can become protonated. Then, water will be the leaving group and will leave the reaction, producing a carbocation. Electrons from the oxygen will form a resonance structure, and water in the reaction can remove the proton to take us back to the carbonyl. So hydrates, or a geminal diol, can be created in acid or base, They're not particularly stable, and in fact, the equilibrium lies so far to the left that in these reactions, we're primarily going to have the original carbonyl group. Now, what if we replaced in all of our reactions the water which we've used with alcohol? So here I have an alkoxide ion, a negatively charged alcohol group, and this will behave exactly the same as the hydroxide. The alkoxide will attack the base of the carbonyl, kicking the electrons onto the oxygen. From here, our new alkoxide ion can grab a hydrogen from a protonated alcohol in the solution. This gives us a group that looks extremely similar to a hydrate. However, our two functional groups are not alcohols. Instead, we now have an alcohol and an ether. This is called a hemiketal. The hemiketal can also be reversed. Alkoxide ion can remove the proton from the alcohol, producing a new alkoxide in our substrate. The electrons in the alkoxide can move into the single bond and remove the ether group, bringing us back to our carbonyl. For this reaction, we used a ketone as our substrate. However, if we had used an aldehyde as our substrate, our product wouldn't be a hemiketal. It would be a hemiacetal, where one of the carbon groups is now a hydrogen. We can also run this reaction in acid as well. Our carbonyl group can grab a proton. Resonance will occur. But now, instead of water attacking our carbocation, our alcohol will attack the carbocation. More alcohol present in solution will remove the extra proton, and this will get us to our hemiketal or hemiacetal, depending on our original substrate. This reaction can also be reversed. The newly formed ether group will be protonated. Then it will leave, giving us back our carbocation. The electrons in the alcohol will form a resonance structure, and the alcohol present in solution will deprotonate, bringing us back to the carbonyl group. Just like with our hydrates, hemiketals and hemiacetals are not particularly favored in the equilibrium, for the same reason as hydrates, that the entropy is far greater to the left of the reaction. However, we can shift this equilibrium if our carbonyl group and our alcohol come from the same molecule, like this one. When this is the case, you have a single molecule forming a single molecule, so your energy and your entropy tend to be roughly the same. When your carbonyl and your alcohol are in the same molecule originally, a ring will be formed. If that ring is a 5 or 6 membered ring, this product is often preferred as these rings are generally stable. Now let's look at that reaction again between a carbonyl group and an alcohol in acid. There is one particular step in this reaction that is vital for understanding ketals and acetals. Here we arbitrarily chose to protonate the ether, but we could have just as easily protonated the alcohol. What would this reaction have done if that was the case? Well, from here, we would have our ether group, which I've now designated without the R, and a diprotonated alcohol group, which can easily leave as water, forming a carbocation, which is resonance stabilized, and our carbocation could be attacked by more alcohol present in the solution. The alcohol would then be deprotonated, and this would give us a new product, a product that has two ethers, a geminal diether. This is a ketal. If this product had been made starting from an aldehyde, that would be an acetal. Here are the 5 main groups that we've discussed: hydrates, hemiketals and acetals, and full ketals and acetals. With hydrates and hemistructures, we can make all 3 of these products using carbonyls in either acid or base. We can also reverse them in acid and base. Our equilibrium favors the carbonyl group due to entropy, so hydrates, hemiketals, and hemiacetals are rarely found in solution. However, we can shift the equilibrium if the carbonyl and the alcohol come from the same structure. And moreover, if they come from the same structure and the product has a 5 or 6-membered ring, the product will be favored. Ketals and acetals behave similarly. However, they can only be made and reversed in acid. The equilibrium favors the carbonyl group due to entropy, but we can shift the equilibrium if the carbonyl and alcohol come from the same molecule, or if both alcohols come from the same molecule. So ketals and acetals tend to be favored if we can get our functional groups into the same structure. It's also worth pointing out here that if you have carbonyl groups and alcohols in the same structure, and you're running the reaction in acid, if you're trying to stop at a hemiketal or a hemiacetal, your reaction will continue to the full ketals and acetals, as the equilibrium will continue as our reaction proceeds. Here's an example of our 2 alcohols being in the same structure. So we took 2 molecules and we turned them into 2 molecules, with one of them having a 5-membered ring, so fairly well preferred. This shifts the equilibrium in the forwards direction. Make sure that you can see that this is a ketal group. I have 2 carbon-based chains on either side of a carbon, and on that carbon I have 2 ether groups, a geminal diether. It just so happens that in this case, the 2 ether groups are connected to one another. Here's another example of a more complex structure. In this case, the equilibrium is shifted quite far to the right due to entropy, as 1 molecule became 2 molecules. Notice here that once again we have a full ketal. I have 2 carbon groups, and on a carbon I have a geminal diether. Understanding this reaction mechanism in the forwards direction is fairly simple, as our alcohols are attacking the base of the carbonyl. But understanding the reaction mechanism in reverse is slightly more complicated, so we'll take a look at that. In this case, I have my ketal, and I want to show this reaction in reverse, going back to the original carbonyl group and alcohols. First, one of the oxygens in the ethers will become protonated. Remember that we can only run this reaction in reverse in acid. Then, the protonated oxygen will leave the carbon from which both of the ethers were originally attached. This will create a carbocation. This carbocation is perfectly stable because of the resonance due to the electrons on the oxygen next door. There should be some water or some alcohol floating around in the solution, likely water, which can attack the carbocation. The water can then remove a proton from the protonated water structure, leaving an alcohol. Next, We want to remove the second of the ethers because our goal is to get back to alcohols and a carbonyl. So we will protonate the ether. The ether structure will leave, leaving behind a carbocation, which is stable due to the resonance. Lastly, the water will deprotonate this oxygen, returning us back to our carbonyl group.